Hello viewers and welcome to our online lesson in Form 2 Chemistry. I am your online teacher Steve Gitau and we are on our channel at Steve Gitau 3660. This is a series of lessons that we have been looking at in terms of helping our students understand more on the challenging topics in our chemistry lessons. Viewers, we have put this material in form of the playlist, and in the playlist we have videos for Form 2 Chemistry and Form 2 Mathematics, Form 3 Chemistry and Form 3 Mathematics, and so on, from Form 1 up to Form 4. Also, the videos are available on the general platform. So welcome and kindly subscribe on the channel, share the videos, comment, and feel free to give me the feedback so that we may grow the channel. In our today's lesson, we shall focus on structure and body. We look at structure and body. And what shall we have in our lesson? We shall discuss the various types of bonds, the structures those particular bonds form, and we give examples on some of the substances that do possess or do have those bonds and those particular structures respectively. After that, we shall also look at common types of bonds, and we shall do a comparative study so that we can identify where these particular bonds are and how they are formed. Join me up to the end of the lesson. Let's look at number one. What is a chemical bond? We are saying that this is usually a mutual force of attraction between atoms, at times between molecules or particles. In this case, when we are talking about the mutual force of attraction between atoms, we are referring to that bond as the bond between one atom and another one. For instance, the bond between sodium ion and a chloride ion. What kind of a bond is there? At other times, we have a bond between a chlorine atom and another chlorine atom. What kind of a bond is that? Other times, we have bonds between molecules. For instance, a water molecule may have a certain kind of a bond and between it and another water molecule. That is the kind of thing that we are talking about. Now, what then is a structure? You find that a structure comes from a bond. There are some kind of bonds which repeat several times. That one bond is repeated several times, creating a regular pattern, and that forms a very extensive kind of a substance, and that is a very good example of what a structure is. In other cases, structures are not huge. However, since there is some attraction between one molecule and another, however weak, we still refer to that as a structure. So you'll find that the structures will be differentiated by the size of the resultant substance and also the strength between one molecule and another molecule. That will create differences in the kind of structures that we shall be looking at today. Now, to help us cut through that topic or that subtopic on bonds and their respective structures, we have a question here. The question says, give the various types of bonds. So we shall list down the types of bonds that we have there, their respective structures. What structures does each one form? And to help us understand very well, we shall give an example of a substance that has that kind of a bond and that kind of a structure in real life situations. Welcome, and let's go into the lesson together. Number one, the first type of bond is the very common type of bond that we call ionic. An ionic bond is a kind of a bond that is formed between atoms when one atom shares its valence electrons with another. The moment it shares its valence electrons with another, that atom that is sharing its or giving out its electrons become positively charged. The atom that receives those valence electrons become negatively charged. Now, there is a force, an electrostatic force, between the positive charged ion and the negatively charged ion, as we had said here, a mutual force of attraction. So, in the ionic bond, there is an electrostatic force between the negatively charged ion and the positively charged ion, and the two now combine to form an ionic kind of a bond. Ionic bond usually generate what we refer to as a giant ionic structure. This is a structure which is an extensive or continuous repeated pattern of the individual ionic bonds. If you take, for example, sodium chloride, when it forms the bond, a sodium ion is bonded to a chloride ion. This pattern is repeated such that every sodium ion is surrounded by 6 other chloride ions, and every chloride ion is surrounded by 6 sodium ions. And that pattern repeats outwards extensively, creating a very large structure, what we are calling giant. The word giant here symbolizes a big substance formed. Which are the examples of substances that form ionic bond and giant ionic structures? Generally, the metals, when they combine with the non-metals, will form such substances. Very common, we have sodium chloride. Sodium chloride. We can have its sister element, potassium chloride. Potassium chloride. We have various oxides of the alkali metals. We have oxides of alkaline earth metals, the likes of magnesium oxide. We have sodium oxide, aluminum oxide, and so on. So basically, the ionic bond is formed when the metal, the cation, having transferred its electrons to an atom which we are now calling the anion. The two with positive charge attract the negative charge and they form an ionic bond. Number 2, we have covalent. A covalent bond. Covalent bond are formed when an atom shares. The key word here is share. It shares its valence electrons with another atom. That sharing creates a bond. We have 2 different structures that are formed from the covalent body. The first one, A, we call it giant covalent. Giant covalent, or also referred to as giant atomic. Giant atomic. So this is, as we had hinted earlier, the word giant signifies large and extensive bonds that are formed in a repeated pattern. Some of the substances that form covalent bonds include, we have diamond. We have diamond, and we also have graphite. We also have silicon 4 oxide. Silicon 4 oxide. These are examples of substances that form giant atomic or giant covalent structures. In B, we have covalent bonds forming what we call molecular structures, known by another name, simple molecular. In this case, the word simple, contrary to giant, signifies small in size, and also metamorphically shows that the bond energy is literal, unlike in the giant whereby the bonding encompasses a lot of energy. Substances that have simple molecular structures or molecular structures include most of the gases, especially so the halogens. So here we can talk about chlorine gas. We have oxygen gas. We also have gases like carbon oxide. So as we had hinted earlier, the structure is between one molecule and another. The bond between one molecule of oxygen and another molecule of oxygen, and so on. So we refer to that. We have that repeating pattern created here. So this kind of a bond here, we are saying, is not as strong as what we find in the giant ionic structures. In number 3, we have a type of bond which we call metallic. As the word suggests, this is a bond that is special amongst metal atoms. You find that metals have the valence electrons attracted so strongly by the positive nucleus. That bonding between a sea of mobile electrons on the outer, attracting the valence electrons, attracting the positive or attracted by the positive nucleus. The sea of electrons attracted by the positive nucleus creates a very strong bond amongst the atoms, and this one is found amongst the metals, the likes of sodium, aluminum, potassium, and so on. So this, in a giant form or in an extensive form, forms giant metallic structure, and this one is in metals like sodium, aluminum, magnesium. So basically, this is reserved for the metals. We have other kinds of bonds which may not be as strong as the first 3. And number 4, we have hydrogen bonds. Hydrogen bonds are a special type of covalent bond that is found in substances that have a hydrogen ion attracting a negatively charged atom of another molecule. So it is very important, viewers, we note that substances that form hydrogen bonds primarily have a hydrogen proton which attracts another negatively charged atom of a neighboring molecule. And that we find that usually hydrogen bonds do not go to the level of forming giant structures, but are in the molecular or simple molecular category. Substances that have hydrogen bonds include water. We also have a substance like ethanol. We are talking about H2O. Primarily, water may have the ions H positive and OH when it ionizes. We have ethanol, carbon, CH3, CH2OH. You can see the hydrogen here may form hydrogen bonds with another molecule with another molecule of a different variety, whereby the hydrogen bonds with another atom which is negatively charged, that way creating a hydrogen bond. We have other simpler cases of covalent bonds, which we call the dative or coordinate bond. Dative or coordinate bond. This is also a special kind of covalent bond whereby the electrons being shared are donated by one of the atoms that form the bond. I do that again. We are saying in a dative bond, the electrons being shared are given out by one of the atoms that that is forming the bond. So it is not a case of mutual sharing. The electrons are donated by one. And that case, if we may start with examples, it is found in the ammonium ion, whereby a hydrogen proton comes and shares the electrons from nitrogen, the lone pair of electrons from nitrogen, without it producing its own electrons. We also have the hydronium ion, whereby also a hydrogen proton bonds with the oxygen and it uses the electrons from oxygen without bringing its own electrons. So we are saying that this coordinate bond, the substances that usually form the coordinate bonds are usually in the simple molecular structures category. They do not go to the giant structures category. They are basically simple molecular. Number 6, we have a relatively weaker kind of a bond, although very, very common, which we cannot ignore. And this kind of a bond is actually a force, and we call it van der Waals forces. The van der Waals forces is a special type of bond that exists between molecules. So I want to underline that. It is not between atoms, it is between molecules. Say, between one molecule of iodine and another molecule of iodine. So one molecule of iodine has van der Waals forces between it and another molecule, such that on literal warming, the van der Waals forces break and the iodine molecule sublimes. That is why subliming requires very little energy to break, because the van der Waals forces that holds the two molecules of iodine together is relatively a weak bond. So we are seeing by comparison here, you can say van der Waals forces are relatively weaker when compared to the hydrogen bonds. What we are saying is hydrogen bonds are stronger when compared to van der Waals forces. However, the hydrogen bonds are not as strong as the covalent bonds. Covalent bonds are stronger than the hydrogen bonds. Hydrogen bonds are stronger than the van der Waals forces. You find that, therefore, substances that have van der Waals forces usually form molecular structures. And they include, we have iodine. The iodine molecules have van der Waals forces or between one molecule and another. We also have the compound ammonium chloride. Between one ammonium chloride and another, we will find those molecules have some van der Waals forces. And that is why you find these two substances do sublime. By subliming, that is the change from the solid state direct to gaseous state, meaning just on little warming, you are able to break the force of attraction between one molecule and another. So viewers, we have had a very good and interactive session in terms of the various body types, the various structures, and examples of some of the substances that have these bonds and these structures. This list is not complete. because we can put in more substances that have this kind of bonds and this kind of structures. In part 2 of this lesson, we shall look at a comparison of common substances that have similar similar elements, but they have different compounds. We are talking about compounds like carbon 2 oxide compared to carbon 4 oxide, ammonia and ammonium chloride, water and hydroxonium ion. And also we can compare, which are similar, say sodium oxide and sodium chloride. That is in our question number 2. In our question number 2, we are looking at a question here which requires us to draw dots and a cross diagram that show the bonding in carbon 4 oxide and in carbon 2 oxide. This will enable us to be able to understand what kind of bond type is found in carbon 4 oxide, that is in CO2, and in carbon 2 oxide, that is in CO. Now, the most important thing to understand first is the number of valence electrons in each atom. You find that in this case, carbon has the arrangement 2, 4, while oxygen, each of these oxygen atoms have the arrangement 2, 6, and this one 2, 6. So the big question is, how do the atoms share out their electrons? Now, straight away you find that the innermost 2 electrons are not involved in bonding, so we need not show them here. We shall focus our attention on these 4. We start distributing them. This carbon atom donates 2 electrons to the oxygen atom. By it donating 2 electrons to the oxygen atom becomes stable at 2,8. Now, on the other hand, the oxygen also donates 2 electrons. Maybe I can show the electrons from oxygen as the dots, so that we are able to have dot and cross. Now, this oxygen, after having given out 2, it is left with the 4. And at this point, if you count on this oxygen, in total, it has 1, 2, 3, 4, 5, 6, 7, 8. It is able to have 8 valence electrons on its outermost energy level, having 2 being shared by or from carbon. On the other hand, in a similar way, we have this oxygen give out 2 electrons, and it is left with 4 electrons. Originally it had 6, it shared 2, and it's left with 4. The carbon on its part shares its remaining 2. It had given out 2, it was left with 2, it shared the 2. We said the 2 are not involved in bonding, we are bonding the 4. That means if we look at carbon, the carbon has a total of 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons on its outermost energy level, which are being shared from the 2 oxygen atoms. The same case with this oxygen atom. It has 1, 2, 3, 4, 5, 6, 7, 8. That molecule has all its atoms being stable with a stable octet configuration. So we are talking about the carbon having a double bond between the oxygen atom. So this is a normal covalent bond, whereby all the electrons are being shared in equal measure, the electrons that form the bond. Let's look at what happens in carbon to oxide. The carbon, once more, has 2, 4. The oxygen has 2, 6. How is the bonding there? In this case, you find that carbon donates only 2 electrons. Out of its 4, carbon donates 2 electrons only. It is left with the 2. We agreed that these 2 are not involved in bonding, so we use the 4. Out of the 4, 2 are left and 2 are given for sharing. Oxygen on its part gives out 4. So the first one, we use the dot for oxygen and another one here. However, since oxygen gives 4, we have 2 others here. And it is left with the 2, since it had a total of 6. 1, 2, 3, 4, 5, 6. However, at this point, oxygen has a stable octet of 1, 2, 3, 4, 5, 6, 7, 8. A total of 8 electrons. And the same case with this carbon. It has 1, 2, 3, 4, 5, 6, 7, 8. It has a stable octet. However, as you can see, some of the electrons being shared are originating from one of the atoms. This is a kind of covalent bond which we call the dative bond or coordinate bond. It can be best illustrated by showing the bonds as carbon, normal covalent bond, that is this bond, and normal covalent bond, that is these 2, and we have a dative bond. In this case, we are going to have the electrons being shown as having come from oxygen to carbon. So we show with an arrow the dative bond. This is the dative bond, which is basically this one. This is a dative bond, and we are referring to the 2 electrons donated by oxygen to carbon for sharing. Unlike this kind of a bond, which is normal covalent. Equal sharing, but here the electrons being shared are coming from oxygen. That way, we are able to compare the bonding in carbon 2 oxide and in carbon 2 oxide and in carbon 4 oxide. Viewers, let us look at another substance or a set of 2 other substances that have similar elements, but the bonding is different. This is in ammonia and in the ammonium ion. Symbolically, we show ammonia as nitrogen bonded to 3 hydrogen atoms, while ammonium is shown that way. Nitrogen bonded to 4 hydrogens, but with a charge. Now, let's start with here. In the bonding for ammonia, you find that nitrogen is of the arrangement 2,5. It has 5 valence electrons. So we are going to have a molecule of nitrogen, and that molecule will have 5 valence electrons. So we have 1 there, we can have another one here, another one there. Those are 4, and we can have 5. Now, the valency of nitrogen is 3. It requires to bond with 3 other atoms. These atoms come with an electron each. So we have hydrogen coming in with its electron. So this is a hydrogen atom. It comes with an electron. We put X. We have another hydrogen atom. it comes and shares its electron there. We have another hydrogen atom, and it bonds covalently, and that is the nature of it. Symbolically, we are talking about nitrogen bonding with hydrogen, with hydrogen, with hydrogen, and it's left with what we call a lone pair of electrons. This pair of electrons are there, and that is the kind of bonding in an ammonium molecule. Let's look at what happens in the ammonium ion. In the ammonium ion, it is a very simple case of a hydrogen proton attracted to an ammonia molecule. Remember, the ammonia molecule has a lone pair of electrons. Now, what is a hydrogen proton? The basic understanding is that in a hydrogen atom, there are 1 proton, 0 neutrons, and 1 electron. Now, when a hydrogen atom loses its electron, when it loses its electron, it is left with just 1 proton. Protons are positively charged, and that is why the hydrogen is shown as H positive. It has only the protons, 0 electrons. Since a covalent bond is a combination of 2 electrons, the hydrogen bonds at this point. We illustrate this one as we repeat on the ammonia. This time around, I'll be a little bit fast since we know how it is. So that's first hydrogen, the second hydrogen, the third hydrogen. And we show this first. The electrons from nitrogen are like that. This is hydrogen. We have the first one. We have hydrogen here. The dots are the electrons from nitrogen. Then we have bonding electrons from hydrogen, and they are there. However, when a hydrogen proton comes in, it bonds and uses these valency electrons from nitrogen, and the hydrogen proton takes the 2, and that way we have a dative bond. We have a dative bond. Since the hydrogen proton comes with a positive charge, that positive charge spreads throughout the molecule, and we show the molecule as having a positive charge at that point. This can be shown in a reduced form as nitrogen bonding with hydrogen, with hydrogen, with hydrogen. That is the original ammonia. But the nitrogen gives a dative bond to a hydrogen proton, and the whole molecule here, the whole molecule has a positive charge. That is the kind of dative bond, normal covalent bond. This is a combination of the 2 types of covalent bonds that we talked about. In the water molecule, the situation is similar, whereby we have oxygen at 2, 6, and hydrogen at 1. Hydrogen is equal to 1. Such that the water molecule being composed of, that is, we are talking about H2O, the oxygen bonding covalently with the 2 hydrogen atoms. The oxygen bonds covalently with the 2 oxygen atoms, and when this is hydrogen here, you find that if we use the valence electrons only, hydrogen contributes 1 electron, while oxygen contributes 1 electron for that hydrogen-oxygen bond, and the oxygen is left with 4 out of the 6. So the oxygen is now stable at 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And the hydrogen has a stability of the duplet, 2. So both of them are stable. And you can illustrate this one as oxygen, a bond there with hydrogen, a bond there with another hydrogen, and it is left with two lone pairs, two pairs of electrons, one pair here, another pair there. Right, what about a hydroxonium ion? In a similar way, a hydrogen proton attacks a water molecule or combines with a water molecule, and the hydrogens become 3, H3O. The hydrogens are now 3, but because this came with a charge, positive charge, like we have explained there, the hydrogen proton has no electrons, just a proton. It shares one of the electrons on this one. So we show this one well as oxygen, and here we can form the hydrogen. We have the hydrogen here, such that the water molecule, that's oxygen, will have the hydrogen will give an electron each. Oxygen gives an electron, and it is left with the 4 unpaired electrons. A hydrogen proton comes and combines with those and creates a positive charge in the molecule. And that is what we are saying. We can illustrate this as oxygen bonding with hydrogen, but here the oxygen gives its valence electrons to be shared datively, and the whole molecule has a positive charge. The arrow shows the electrons being shared are from oxygen only. That way, we are able to show the hydroxonium ion. Finally, we have calcium oxide. In calcium oxide, viewers, it is important to realize that this is different from what we have done above. The calcium at 2882 compared with chlorine at 287, this is a metal, this is a non-metal. The bond will be ionic. The innermost electrons, 2, 8, and 8, are not involved in body. So what will happen is, calcium requires to gain 1 electron from calcium. Chlorine, requires to gain 1 electron from calcium. So calcium will transfer its 2 electrons to chlorine. We are going to show just the 8 electrons in calcium. So this is calcium. And here, after transferring these 2, calcium is left with 8 electrons in its outermost energy level. So in both cases, we are going to show this is now calcium ion at 288. These 8 are the last outermost energy level, and you realize that the atom changes to an ion with a positive 2 charge. It is positively charged, and it is mutually attracted to 2 chloride ions. Since it is important to note that the formula for calcium chloride is so: the 2 electrons are transferred to 2 chloride atoms, since 1 chloride atom can only take 1 electron. So you need 2 chloride atoms. And so we show a chlorine atom, and we have agreed that we are going to show only the outermost energy level electrons. Now, chlorine had 7. So these are 1, 2, we can pair them. 1, 2, 3, 4, 5, 6, and 7. At this point, very important, the calcium transferred its electron to chlorine, and chlorine now has a negative charge. Two of them now receive the 2 electrons from calcium, and at this point, the chloride ion is at 287. So there are 2 of them. That's why I have shown 2. Another way of showing this is where you put 1 calcium and 2 chlorine or chloride ions. But this is a simplified version of showing the ionic bonding. So viewers, very clearly, I intentionally did show the ionic bonding so that we can have a comparative study with the sharing. In sharing, we put the 2 electrons together in a common area. But here, we are showing complete transfer. The dot, meaning the dot showing an electron from calcium is transferred to chlorine. That is the essence of dot and cross diagram, and that is how ionic bond is vis-a-vis the covalent. And once more, we are also seeing the covalent, normal covalent against the dative form of covalent body. Viewers, we've come to the end of our lesson today on structure and body. I hope it has been very interactive. I would like you to subscribe, share, and comment on the video. Should there be a structure that you'd like us to draw, put it on the comment section and I will reply to you. I'm very grateful for your joining me in this lesson, and I look forward to posting more videos in our online lesson. Remember, this is a series of lessons that we shall be putting up for our Form 2 students, and they are also very suitable for the students in upper forms, in Form 3 and Form 4, especially those who are preparing for their exams. Coming up next, we shall have a lesson on salts. In this lesson, or during this lesson, we shall examine methods of preparing salts, various types of salts, and even writing equations, both ionic and the normal complete equation for the formation of that particular salt. I look forward to joining you and you joining me in that lesson. Otherwise, thank you and God bless you.